Okay, here I just want to illustrate the use of the HP180a's dual time base. It's delayed trigger time base. Okay, so I'm going to have to be varying the light so that you can see the controls of the scope and the trace, okay, at the same time. Now, you won't be able to see them at the same time. Alright, so what we've got here is we have the Tar Baby circuit under power. Okay, this is the Tar Baby circuit. That is the one that is identical to the one in the Ainsley paper number 2. Okay. For some reason I can't find the circuit diagram right now. It's this circuit diagram, except this is Q1 and this is Q2 times 4 over here. Alright, just the same. Where'd that thing go? Maggie? What did you do with that circuit diagram? The dog took it, I know. Anyhow, it's running, and the F43 function generator is pulsing it at 2 kilohertz, and all negative going pulses, and you can see that up there. This is 0 to negative 5 volts, and when it goes to negative 5 volts, it causes the oscillations. All right, so 2 kilohertz. I've got the time base of the scope, the main time base of the scope, set at, can you see that? 0.2 milliseconds per horizontal division. Alright, so 0.2 milliseconds per horizontal division. Alright, and if you take and just move that trace over a little bit to where it starts at 1 division, you can see that it takes 1, 2, and just about a half, 2.5 full divisions to go 1 full cycle. And so 2.5 times 0.2 is 0.5. So it takes half a millisecond to go 1 cycle. And if you do the math, that comes out to just about 2 kilohertz, right? Okay, so that's the frequency of the main pulses that are being given by the F43 function generator. But suppose we want to resolve this mess in here and see what its frequency is. Well, if we just simply take the scope's main time base and crank it down to where we can actually resolve that, we lose a lot of information, because now we don't know where we are with respect to the pulses or anything like that. So let's just leave this at where it was, at 2 milliseconds per division, and let's use the delayed trigger feature. Okay, so the way that you do this is this outer knob here. Sorry about the light. Let's see if I can show you that. This still can't really see it, can you? This outer knob controls the delayed trigger time base. So I'm going to set it to 1 microsecond per division. Okay, and we'll have the sweep mode auto and the delayed trigger level over here set to internal. All right, so now you can see, or you should be able to see, can you see that? Is that visible? There's a little brighter line right across there. Let me turn some lights out. Okay. Is that showing up? There's a brighter line. Adjust intensity a little bit there. Okay, so you can see that brighter line there. Well, that brighter line is controlled by this multi-turn knob down here, and I can move that line across the trace, right, and move it to the other part over there. All right, so that line and the thickness of it tells me where the delayed trigger is going to look. So if I vary that outer ring here that's now set to 1 microsecond, you can see that the thickness of that line changes. So we're looking at, right there, we're looking at 1 microsecond's worth of this whole trace, which is 2 milliseconds per division. Alright, so now let's go ahead and expand that by turning this little knob here to there. Excuse me, I have allergies to the pollen that's in the air right now here in South Texas, so I'm kind of choking up right now. So let me turn the intensity up a little bit. So now you can see where that line, that little bright line was, is now split out. We're triggering right there, and we've expanded the area inside that white line to show its frequency at the delayed time base of 1 microsecond per division. So these guys over here up to this point, that's 2 milliseconds per division, and then starting here with these traces, that's 1 microsecond per division. So by counting pulses, right, we can go, let's turn the intensity up a little bit more so we can see what we're doing, and let's put 1 pulse right on a division line like that, and now let's count from there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's another division line right there. So we have 12 pulses in 1, 2, 3, 4, 5 microseconds. So do the math. 12 divided by 0.000005 comes out to, I don't know, what does it come out to? Anyway, if you do that division, you will get the frequency of this oscillation. Okay, and if I go back to the little knob here and vary where that trigger is happening, I can even get just the edge of it, maybe just get the edge, and show how that guy develops, what it looks like just as it makes the transition. And see if we can find the other edge. I might have to look at a different trigger. Let's see here. Okay. Oh, somebody unfocused my scope. Alright. I can't quite find that edge. Let's see here. Whoops. It's not going to show me the edge. How about the other edge? Yeah, I can see that edge, but I can't quite get it to show me the beginning. Let's see. There it is. There is the beginning. Right there. Okay. That's the beginning. And that's the end. Right there. So the delayed time base feature is very, very useful for doing things like this. And that's one of the reasons why I love my HP180a oscilloscope. You can't do this kind of stuff on many digital oscilloscopes. Cheaper ones, anyway, you can. Alright, thanks for watching.